Hello everyone. In this video, I'm going to walk you through this question SQ2 of our supplemental antenna exercise. We are given four equally excited isometric antenna at four corners of the rectangular region. And as you know, you have many other ways to solve the problem. You can just use the usual formula, but it's not going to be flexible because the antenna can be anywhere on the two-dimensional plane. And if you do that, then for a rectangular uh, panel array, it will be okay. But if there's some variation, then it's going to be very tricky. So I suggest you use the smarter technique. So let's continue. So let's start. Before moving forward, let's learn something. We know an antenna will radiate our electric field, and the electric field is usually given as, for example, E naught, and then e to the power j k, and then d, and then make it R. R is easier to understand. So this is the kind of antenna, the typical the typical expression for the far field, where k is the wave number and R is the distance or whatever. So R itself is a distance, and this distance can be a combined value. Yeah, as long as you have dot product, then you will have a scalar distance here. R is a scalar, and this is also a scalar. And remember the definition of dot product. Dot product is a projection of, in this case, dot product of R is a projection of R in the direction of R naught. So this is something we want to know. So let's say R naught, it is a, let's say we have a three-dimensional planes, and we have Z, we have a X, and we have a Y, and we have a randomly chosen target, and this is represented by R naught. And let's take a look here. What is the XY coordinate, XYZ coordinate of this R naught? Yeah, so the X coordinate, let's take a look. The Z coordinates first. We have a angle of elevation theta, And we also have a position identified by the angle of azimuth phi. So let's take a look here first. The height here, if my understanding is correct, the height here is uh, the arrow log and then cosine theta. Now let's take a look in the x coordinate and we try to calculate the x coordinate. So if you use perpendicular projection here, then the value here of this length here is arrow log sine theta, right? Now what we can do here is we can use cosine theta, and this become x. So x is done, z is done, and what is left is here y, yeah, y, and y is arrow log, and then this one sine theta. So we get all three coordinates. Then uh, we can say arrow log, the vector arrow log is equals to x and then arrow log sine theta cosine gamma and then plus y and then arrow log and then sine theta and then sine phi. And then we plus the last term z. Z is equal to arrow log and then cosine theta, this one. So obviously, if you want to know the unit vector pointing to this direction, the direction of arrow log, then we can say arrow log head, and this will be equal to arrow log divided by the magnitude of itself. And in this case, if you derive everything, so we get this. So obviously, if you want to know the unit vector in the direction of the propagation, uh, then we can write it in this manner. Now, for exactly the same reason, if you have any uh, antenna array in the XY plane, for example, in this case, you have one here, one here, one here, one here. Then we can use the individual vector here, and then dot product with this one, and then get the equivalent radiation pointing to the direction of propagation, the direction of your choice. And then we find out the combined electric field. And this is what we can do. Okay, so let's stay tuned. Yeah? So let's write down the formula first, and let me clean up the whiteboard. So let's say here, arrowhead is equal to x and then beta and then cosine theta. and then plus y hat, and then sine theta, and then sine theta, and then plus z hat, and then cosine theta. So this is the vector that we need. And I'm going to clean up the whiteboard. Okay, so this is a very important stuff. So I'm going to highlight it. So this is the randomly chosen the direction, and the direction can be expressed as a coordinate x, y, z, and this is how this is done. Okay, so I'm going to clean up the whiteboard, and we are going to look at the question again. So SQ2. So let's take a look in the coordinate. So we have um, we have y, x. So we are now looking at the two-dimensional plane x, and the angle of theta is not known. So let's say here d, and we have one here, and we have one here, and we have one here, and we have one here. So they are all distant of d. This one is d, this one is d, and this is the origin. So now let's identify the vector. Let's say this is item 1, and this is item 2, and this is item 3, and this is item 4. Now let's work out item 1. Item 1 is R1. R1 is the vector identified by the position of this. The position, right? If you tell me the xy coordinate is d, and if you want to write it in vector form, it is x hat times d plus y hat times d. And similarly, for item 2, for antenna 2, we know the coordinate. It is minus x hat, and then the height has not changed. And let's take a look in antenna 3. Antenna 3, right? We have minus x hat d minus y hat d. And let's take a look in antenna 4. We have x hat d, and then minus y hat d. So now we have managed to use vector to represent the xy coordinates of all vectors or all the antennas. So now, what we need to do is to find out uh, their projection in the direction of propagation. The direction of propagation in the unit vector representing the direction of propagation is arrow not head. So in this case, you can write down here arrow one dot product with arrowhead, arrow log head, and this will give us. Now remember how we can do dot product, right? X hat will never 90 degree, right? Um, uh, yeah, in this case, we just the magnitude of x hat and x hat multiply together, and in this case, d sine beta cosine phi, and then for the y hat, and then d sine beta sine phi. So we have done one, and let's do some simplification on the fly. As you can see here, both terms contain uh, d sine theta. So we can extract it out. And then what we end up with here is cosine e plus sine e. Now let's take a look in the second antenna. Its projection in the yet its far view projection in the direction of propagation can be written as I should say is vector projected to the direction of propagation is uh, vector arrow 2 dot product with arrow 2 head. So in this case, as you can see here, we can say minus d sine theta cosine phi, and then plus d sine theta sine phi, and then uh, we can continue, yeah, d sine theta, and then we can just minus cosine v plus sine v, and we can continue with this process and dot product with arrowhead for the third antenna minus d sine theta cosine phi, and then minus d sine theta sine phi, and then what we can get here is d sine theta, and then we get minus cosine d and minus sine b. And similarly, the process can continue for the last antenna, and d sine theta cosine phi, and then minus d sine theta sine phi, and then d sine theta, and then cosine phi minus sine phi. So we are almost there. Now what we are now trying to do is to reconstruct the uh, antenna the total electric field in the direction of propagation. The total electric field in the direction of propagation is also the antenna, the array vector, and it is equal to E, assuming that the magnitude is 1, and then J, K, R1, and then dot R log hat. And this is how we calculate the distance, the phase in the direction of propagation. And we can continue with this process for the second antenna, and then R2 dot R log hat, and then E, K, R3 dot R log hat, and then E, K, R4, and then R log hat. And then now I'm running out of space, but I can still not easy. So we can now substitute all the actual value. They are all scalar. This bracket term here are all scalar. And it has been calculated here. We can just do a bit of substitution, then our job is almost done. So let's move to here. Yeah, let me clean up the whiteboard. And I presume you don't need this diagram anymore. Yeah, let me clean up here. And we will continue. We will continue up here. So now let's write down the array vector. This guy here is E, K, and we have already calculated. According to here is D sine theta, and then cosine phi. Yeah, let's move this. Let's move this out. And then plus sine phi. So this is the first term, and then we write down the second term, E, K, J, and then this one, D sine minus cosine phi plus sine phi. Okay, and I'm going to write down the remaining two terms as well. E, and then J, K, and then this one, D sine theta, and then plus and then sine. By the way, I make a mistake here. I should write J, K, sine theta, and then cosine theta minus, you have to do it very carefully, sine theta. So this is the whole expression, and you need to Uh, Now we is the matter of grouping. Now let's see this the cost these two terms can group together first, and we extract cosine phi here first, and then what we have left is E J K D uh, sine theta sine phi, and this term here is plus E J K D, and then sine theta sine phi. Yeah, this is now we are now in the right path, at least apparently. And now we are going to combine these two terms very, very carefully. And sine theta, and apparently is you can do cosine phi, yeah, and minus, and then we group it E J K D uh, sine theta sine phi, and this is minus, and then plus E J K D minus, and then sine theta, and then sine phi. So we are almost there now. Now, obviously, you can see the upper term can be changed to cosine and this trunk of expression. The lower term, equivalently, we can do the same. So we can continue very, very easily now. We can do it. So the upper one first. So first we write down K D sine theta cosine phi, and then this one is going to be 2 cosine, and then K D sine theta sine phi, and then plus. And the other terms here is this one, KD sine theta cosine phi, and then we can rewrite this term as 2 cosine KD sine theta, and then sine phi. Okay, now apparently we are almost there, because now apparently we have a common term, right? We have both expressions contain common terms now. We can extract both, and then we can take care of these two. Yeah, but by the way, this is not my style. And also, there's a minus here. So we will extract it. So 2 cosine K D sine beta, psi, b. Yeah, we extract this term, and then obviously you can immediately see that this is cosine. Uh, so the two cosine, yeah, these two terms combined will be cosine. K d sine beta cosine phi. Okay, so we are almost there now. Um, so the answer here is 4 cosine k d sine theta sine phi, and then cosine kd sine theta cosine phi. So this is done. We can use other method as well. We just need to substitute the y value, uh, but this is the most flexible technique. So as far as this question is concerned, I think it is done. If you have any further question, please leave your comments to the comment sections. Okay?